And my name is Prakash Gupta, and this is my Physics 2211 Lab 5 video report. So the goals of our labs are to develop simulations and analyze resultant data to find experimental values and analyze systems. This lab was a choose-your-own-adventure lab, and the situation that I chose was, would the heat generated through work done on by drag on a block of mass m with initial temperature T, as it falls from a height h is governed by a drag coefficient b, be sufficient to melt the block of ice? The principles at play here are Newton's laws of motion, gravitation, the update equations, drag, work, and thermal energy. The result that we found is that this is not a suitable situation for closed script, and that it's essentially impossible to achieve this for unit values of all of those variables. So let's look at these major principles, and we've got our gravity near the surface of the Earth, we've got our drag force, a Newton's second law, work, which we're approximating to be F delta T, thermal energy, which we are accounting for the heat of fusion, which is the heat given off or required to undergo a phase change. And we've got our update equations, which are pretty standard at this point. So let's look at the simulation. We built off the starter code for lab 2, but we had some key differences, namely that we eliminated the graphs for the x direction as we assumed that our block is falling straight down towards the Earth's surface, and instead we replaced that with a graph of work against time, which is our the amount that of energy that's work due to drag. We've also changed our initial conditions to take user input so that we can test this for a variety of different initial conditions, being mass, drag coefficient, and initial temperature. At the bottom there, we can see that a calculation for the total energy needed, the thermal energy that needs to go into the ice, and that's calculated using our MC delta T and our heats of fusion using known values for ice and water. Regarding the simulation, we also set our initial work done by drag to 0 and add that as a parameter to increment. And in our loop, we speed it up a whole lot and we record our old position so that we can calculate that delta T later, delta X later. And we have essentially our same calculation for the force using both our drag and our gravity and our update equations. And then we graph our positions and we graph our values on the plots. And that gives us our simulation. We also changed the runtime setup so that it would run until the ball hits the ground, because that's, the block of ice hits the ground, because that's what we care about, that it melts before hitting the ground. So looking at data analysis, a brief calculation shows that it would take 3 times 10 to the 6 joules of energy to vaporize a kilogram of ice starting at 0 degrees Celsius, which is optimal here. And considering the known drag constant of ice through air, which is approximately 1, the block would need to fall at escape velocity for 306 kilometers. So let's just estimate that it needs to fall from a height of 307 kilometers above the surface of the Earth. And we can see some brief data analysis from the graphs generated by our flow script model. But as you can tell from that work versus time graph, we're not really getting anything done in 10 seconds, nor were we really in 10 minutes. And that has some interesting implications on our, conclusions here. And it is incredibly unfeasible to attempt to model a block falling 300 kilometers at 10 meters per second. And that's just impossible for GlowScript to handle within a reasonable amount of time. So we also have one other source of error for the situation. We're assuming that no energy is being transferred as heat between the surroundings, the air and the ice. So we're not really accounting for that thermodynamic interaction. We're only accounting for heat due to drag. So some what ifs. So what if we had other values for initial temperature and mass and all sorts of other stuff? We can use this simulation to model those as well if it was, powerful enough. For instance, we can see that a standard ice cube, the kind that comes out of your fridge, is a lot easier to model because it only needs 2 times 10 to the 4 joules of energy. And that's not a big help here because that's still totally unfeasible to model with this with GlowScript, but we can still analyze qualitatively what this kind of means. So from our rough calculation, It's certainly not possible to vaporize a kilogram of ice under the conditions given. 306 kilometers is far above the Kármán line, which we may use to denote the Earth's atmosphere. And uh, arguably, uh, we can just conclude, 306 is triple the Kármán line's height. It is not possible to do that while falling through the Earth's atmosphere. Certainly, it may be possible for smaller volumes of ice. Thank you.